Our dataset contains a total of 100 samples, neatly organized into 20 groups, with each group comprising 5 samples. This structure is really important for our group-based cross-validation. This setup is crucial because it helps us understand how our model performs when considering the relationships within each group. Imagine each group representing data from a single person. Then, we would want to ensure that the data points from the same individual are not split across training and testing datasets, which is what our cross-validation method aims to achieve. We're using a technique called GroupShuffleSplit for cross-validation. This is a special type of cross-validation designed to handle data with groups. It makes sure data from the same group doesn't end up in both training and testing sets simultaneously. Why is this important? Because this could lead to biased evaluations. Imagine trying to test a medical treatment. If you accidentally assign members of the same family to both the treatment and control groups, your findings will be skewed. GroupShuffleSplit prevents this. It keeps data from the same group together, ensuring more accurate evaluations. This option sets up 5 folds, n_splits equals 5, with 20% of the data in the test set for each fold. Test_size equals 0.2. But it's missing a key ingredient. To make it work properly, we need to specify the groups using the _groups parameter. Without it, GroupShuffleSplit won't consider the group structure, treating the data as if there weren't any groups and randomly dividing it. Here, we've added a random underscore state, 42, which helps make the random splitting reproducible. It makes it the same every time. But it still misses the crucial _groups parameter. Again, like in the previous option, the lack of the _groups parameter will prevent the correct group-based behavior. The split will be random, ignoring the groups. It's like shuffling cards without looking at their suits or numbers. You won't get a stratified shuffle. This uses 5 folds and sets the test size to 20 samples. Test_size equals 20, which is equivalent to a full group of data. It's a valid test size. But, guess what? Still missing the essential _groups parameter. It's missing the vital _groups parameter, resulting in a random split, disregarding the group information that is needed for a proper stratified split. Finally, this is the correct option. This time, everything is in place. 5 folds, n_splits equals 5, a test size of 20%. Test_size equals 0.2, and most importantly, the groups parameter is specified. 0, 1, 19, It tells GroupShuffleSplit how to respect the group structure during the split. The _groups parameter, with values from 0 to 19, explicitly defines the group membership of each sample. This allows GroupShuffleSplit to perform the stratified splitting properly, ensuring no samples from the same group appear in both training and testing sets within a single fold. This setup ensures the accuracy and integrity of our cross-validation results. This refers to a technique in machine learning, specifically within scikit-learn, used for splitting data into training and testing sets while ensuring that samples from the same group are not split across different sets within a single fold. Imagine you're dividing students into teams for a project, but you want to make sure that all members of the same family are on the same team. That's what GroupShuffleSplit helps achieve. It's essential for avoiding data leakage when groups represent correlated data like repeated measurements from the same subject. This sets the context. We have a dataset with 100 data points, neatly organized into 20 groups. Each group has exactly 5 data points. This is vital information for understanding how the different GroupShuffleSplit options will perform. Think of it like 20 different classrooms, each having 5 students. The core question is to identify the specific GroupShuffleSplit configurations that perfectly handle this grouped data, ensuring no group members are separated across training and testing sets within the same fold. The key here is to understand how to correctly use the _groups parameter. This option attempts to create 5 folds with 20% of the data in the test set each time. However, it misses a crucial parameter, _groups. Without specifying the groups, Group shuffle split can't guarantee no group members will be separated. It's like trying to assign students to teams without knowing their family relationships. You'll likely end up with siblings on different teams. Similar to option A, this one also has 5 folds and a test size of 20%, or 20 samples. The addition of random underscore state equals 42 ensures reproducibility. The random split will be the same every time you run it. But, again, the critical groups parameter is absent. It will still perform a random split, ignoring the group structure. This attempts to create 5 folds, but with a fixed test set size of 20 samples, which is perfectly valid in this case, 20% of 100 samples. This would be a suitable approach if groups were accounted for, because the test underscore size is compatible with the structure. However, the absence of groups renders this choice also incorrect. Option D is the only correct one. It has all the necessary parts. 5 folds, n underscore splits equals 5 a test size of 20%, test underscore size equals 0.2 and most importantly, the groups parameter, which correctly identifies the group structure via groups equals 0, 1, 19, This is the correct recipe because it correctly provides the group information. So group shuffle split can maintain group integrity. This guarantees that samples from the same group are never split between the training and testing sets within the same fold. This line introduces the core concept, using GROUPSHUFFLESPLIT for cross-validation. Cross-validation is a technique to evaluate a machine learning model's performance by splitting the data into multiple subsets, folds, training on some and testing on others. The group aspect means we're ensuring that data points related to each other, e.g., measurements from the same person, stay together during splitting, preventing bias. Here, we're given the dataset details. We have 100 data points, organized into 20 groups, with each group containing 5 data points. Understanding this structure is key to choosing the right cross-validation strategy. This sets the stage. The goal is to identify which way of setting up GROUPSHUFFLESPLIT will reliably keep data points from the same group in either the training or testing set of any given fold, but not both. This is important to prevent information leakage between training and testing, which can artificially inflate performance metrics. Okay, so we're using a tool called GROUPSHUFFLESPLIT to divide our data for testing. It's a special kind of cross-validation designed to handle data where items are grouped together. Think of measuring the same person multiple times, or samples from the same location. The goal is to make sure that, during our tests, we don't accidentally use data from the same group in both our training and testing sets at the same time. That would mess up our results, right? We're working with 100 individual data points, which are neatly organized into 20 groups, with 5 data points in each group. Think of it like having 20 different classrooms, each with 5 students. We want to split these students to make sure no classroom has students both studying and getting tested at the same time. It's important to keep the groups separate for accurate analysis, you see? The challenge is to figure out how to set up our GROUPSHUFFLESPLIT tool. We need to choose the right settings so it splits our data correctly, making sure no group is used in both the training and testing parts of the experiment simultaneously. This attempt to set up GROUPSHUFFLESPLIT is missing a key ingredient: the groups parameter. It's like trying to bake a cake without flour. It just won't work. Without specifying the groups, the tool won't know to keep them separate. Similar to the previous attempt, this option is also missing the crucial groups parameter. The random underscore state helps make the results repeatable, but it doesn't solve the core issue of group separation. While this one has the correct number of test samples, 20 out of 100, it still lacks the vital groups parameter. So, like the others, the groups won't be kept separate, and that's a problem. And here's the winner. This one is perfectly set up. It specifies the number of splits, 5, the portion of data for testing, 20%. And, most importantly, it includes the groups parameter, which is a list defining each group, from group 0 to group 19. Now, our GroupShuffleSplit tool can do its job correctly, keeping our groups nicely separated in our training and testing sets. So, the only choice that ensures our groups stay separate is option D. The others fail because they don't explicitly define the groups. They ignore the group structure altogether, making them unsuitable for our problem. To reiterate, the groups parameter is absolutely essential for GroupShuffleSplit to work properly. Without it, the tool essentially becomes a regular shuffler, ignoring the critical group structure of your data. This refers to a technique in machine learning used to split data into training and testing sets, ensuring that data points related to each other, like multiple measurements from the same person, don't end up partly in training and partly in testing. It's a crucial step for reliable model evaluation. We're working with a dataset containing 100 individual data points. These are organized into 20 groups, with each group containing exactly 5 data points. This grouping is key because it dictates how the data should be split for cross-validation. This attempts to create 5 folds for cross-validation, with 20% of the data in each test set. However, it's missing a vital ingredient: the groups parameter, which tells the algorithm about the relationships between data points. Without it, the splitting is random and doesn't respect the group structure. Similar to option A, this also sets the number of splits and the test size. The _random_state parameter ensures that the random split is reproducible, giving the same results each time. But, just like A, the critical groups parameter is missing. So it still performs a regular random split and not a group-based split. Here, the test_size is set to 20, meaning 20 samples will be in the test set for each fold. It still lacks the crucial groups parameter to enforce group-based splitting. The algorithm will still perform a random split ignoring the group structure. This is the correct option. It sets 5 splits, a test size of 20%, 20 samples, and importantly includes the groups parameter. This parameter, a list of numbers from 0 to 19, explicitly defines the group structure of the dataset and thus ensures that data from the same group will never be split across the training and testing sets within a single fold, which is what we needed to achieve.